is the fifth lecture on partial differential equation. Today we shall discuss two more cases, two more situations where we solve the Laplace's equation in spherical polar coordinates having azimuthal symmetry. As the first example, we consider a grounded spherical conductor and a point charge q placed outside the conductor. Earlier we have solved this problem in electrostatic courses, in electricity courses, by using the method of images. Here we shall arrive at the result, same result, but we shall solve Laplace's equation. The situation is that we have a conductor of radius a which is grounded one. We choose the origin of the coordinate system to lie at the center of the sphere, and the location of the point charge q may be anywhere outside the sphere, but the situation or mathematics involved gets drastically simplified if one chooses the z-axis in such a way that the point charge lies on the z-axis. This does not robs of the generality of the problem. This is only the clever choice of coordinate system, and if we choose such a geometry that the point charge lies on the z-axis, then this inducing charge will create some charge separation, and the charge separation will have azimuthal symmetry. That is, the charge that will be developed will be independent of phi. Our aim is to find out the potential at a point r. At a point r, in general, the point P will have coordinate r, theta and phi. But if we consider that this line OA and OP to lie in the phi is equal to 0 plane, then the coordinate of P point is r theta and phi is equal to 0, where theta is this angle. Now, if we want to find out the potential at P, the potential at P is partly due to this charge Q, and so the potential at r theta 0, this point, is Q by 4 pi epsilon 0 distance AP. This is the potential at P due to the charges this, plus a contribution phi induced polar potential. That is, this charge will create some charge separation over there, that is, some induction effect will be there, and this induced conductor will contribute something over there. Now, to find out this part, we recall that the solution of this phi induced is obtained from Laplace's equation. So phi induced, if we consider three regions, one is the region ranging from 0 to A. In this region, for internal region, r is less than equal to a, greater than equal to 0. This is the solution of Laplace's equation. So phi induced in the internal region will have the form AL at to the power L PL of cos theta, because in this region includes r is equal to 0 and BL part and the part BL r to the power minus L plus 1 has a divergence, so this part is not there. And for external region, this external region, I must write induced external I induced internal is equal to BL r to the power L plus 1 PL cos theta L is equal to 0 to infinity. So these are the induced part. Here we have assumed that the potential is the solution is so chosen that the potential remains finite everywhere and it goes to 0 asymptotically. Now coming to this part, AP part. For 1 upon AP, this distance can be written as this much is the d vector and this is the r vector, so this is r minus d vector under root, so this is equal to r square plus d square minus 2 twice r d cos theta to the power half minus half. Now there are three regions of interest. One is, let me recall that this is nothing but the generating function of Legendre polynomial, and this can be written as 1 upon r summation over L is equal to 0 to infinity d by r to the power L PL cos theta for r greater than d, and this can be written as 1 upon d summation over L is equal to 0 to infinity r upon d to the power L PL cos theta for r less than d. That is, which one of amongst r and d will have lesser magnitude will be on the numerator, and the quantity with greater magnitude will be in the denominator. So this is applicable for region for which r is greater than d. And for we separate this region. For this potential, we divide the entire region in three parts. One is this one, for which the expansion is this, and the other region which extends from r is equal to a to d. For all this region also, this is the expansion of potential of this part, and for region having r greater than d is this. So the total potential, we write the total potential as this. Potential, I am not writing phi part anymore. So internal region, for internal region, this is kq by d summation over L is equal to 0 to infinity r by d to the power L PL of cos theta plus summation over L AL r to the power L PL of cos theta for r less than a greater than 0. This is the solution for internal points. For external point, PL of cos theta, wherein R is less than equal to D, greater than equal to A. This is the external region, but R is less than or equal to D, and the KQ by R, L is equal to 0 to infinity, D by R to the power L PL plus summation over L is equal to 0 to infinity BL R to the power L plus 1 PL cos theta. This is for R greater than equal to D. So there are three solutions. This is also a solution in the external region. So the external region is divided into two parts, for which R is less than D. So we may assume this to be, this is a sphere of radius D. So this is the solution. This solution refers to this region, and this solution refers to this region. And this solution is the internal region. It has no ambiguity. So these are the solutions for three different regions. Now, the conductor is a grounded conductor. So we have the potential that is obtained from this is 0 on the surface. So we have phi I R is equal to A theta is equal to 0. Oh, sorry, I have forgot to write the value of K. K is the SI factor 1/4 pi epsilon 0. So this is the potential is 0 as it is the grounded one. If we apply this result, we get KQ by D summation over R is equal to A by D to the power L PL plus summation over A to the power L PL cos theta. This is thus always the sum extends from 0 to infinity, and this result is valid for all values of theta, that is, it is an identity in PL, and the coefficient of PL of cos theta gives you KQ A to the power L D to the power L plus 1 plus AL A to the power L is equal to 0, or AL is equal to L plus 1. Now, since the potential is 0, we may assume these to be 0 for all values of L. Now come this AL values, this choice of AL values makes this potential 0 for all L. So the potential is 0 on the surface of the conductor as well as in the interior of the conductor. That is to say, phi I is equal to 0. So this is the values of AL which satisfies this condition. Again, if we would apply the boundary condition on this solution, that is phi E at R is equal to A theta is 0. Now this is the proper solution. So we have KQ by A to the power L D to the power L plus 1 plus BL a to the power minus L plus 1 is equal to 0. This is the coefficient of PL, or we get BL is equal to minus K cube upon d to the power L plus 1 a to the power 2L plus 1. We write it as minus K a q by d times a square by d to the power L. This we write plus K q prime times d prime to the power L, wherein we write q prime is equal to minus a q by d and d prime is equal to a square by d. This is our. So with this, the potential at an external point becomes, with this choice of BL, we have obtained the value of BL to be like this. So the potential at an external point, so far the induced part is concerned, the induced part, the external part, at external point, the induced part, that is this part, is summation over L is equal to 0 to infinity BL r to the power minus L plus 1 times PL. We write for BL KQ prime KQ KQ prime d prime to the power L d prime to the power L r to the power minus L plus 1 PL of cos theta. This part we write as KQ prime by R summation over L is equal to 0 to infinity d prime by r to the power L PL of cos theta. This can be written as KQ by R minus d prime vector. In earlier situation, we have written 1 by R minus d R minus d is equal to 1 by R summation over d by r to the power L PL of cos theta, where R is greater than d. Here this exactly similar situation has appeared as on the right hand side. We have written the left hand side from this. So this represents that this induced part, so for an external point is concerned, as if it is the potential at point R. It is the potential at point R due to a point charge q prime located on z axis at a distance d prime. Now coming to the concept of values of q prime. Q prime is minus aq by d and its location is as this. Now, as per our choice, D is greater than A. So the magnitude of the induced or image charge is less than that of Q. And D is greater than A, so D prime is less than A. D prime is less than A. That is, the image charge is located within the sphere. So to say, whenever we are interested in finding out the potential at an external region, the effect of the induced charges can be replaced by a point charge of magnitude q prime located at a distance d prime, and as the region of interest is lying outside the sphere, the image charge must be placed within the sphere. That is what we have, that is what was our starting point in the method of images. Here we can get a mathematical justification for the method of images. If one wants to find out the potential at an internal point, in this particular case it is 0, then we will see that even if the conductor is not a grounded one, if we want to find out the potential at an internal region, then the image charge must be placed outside the sphere. From that is the boundary which separates two media. One is the internal region of the conductor and other one is the external region of the conductor, as it behaves as a mirror, and we are talking and we are considering that the image, when we place an object in one side of the mirror, the image is formed on the other side. This is the basic concept in the method of electrical images. As the second and last example of today's class, we shall consider a dielectric sphere of radius a placed in an existing uniform electric field. Now a dielectric sphere of radius a, it is placed in an uniform electric field. As we have argued in the earlier class, the calculation will have azimuthal symmetry if we choose the uniform electric field to lie along the z-axis. So we write E0 is equal to k cap E0 vector, and the corresponding potential is given by this. We have elaborated this step in the last lecture. Now, whenever the dielectric sphere is placed within an electric field, some polarization effect will be developed herein, and if we consider a point which is not occupied by any charges, then the Laplace's equation will be satisfied over there. And we know the for spherical symmetry, the Laplace's equation is given by phi internal point is given by summation over L AL r to the power L PL of cos theta for r less than equal to a greater than equal to 0. For external region, for external region, the potential, as we let r tends to infinity, the potential must go to this one. So we write it as C minus E0 RP1 plus summation over L BL r to the power L minus 1 PL, with region of interest is r less than infinity greater than equal to a. So this solution has been obtained on the basis that phi I is finite at all values of r, and in this case we have applied the condition that as r tends to infinity, the potential must go to this value, the potential corresponding to the existing field. Now we have two boundary conditions to be satisfied. The boundary condition is that the tangential components, the continuity of the tangential components of the electric field gives us that a theta is equal to phi e at a theta. So that we have from this part summation over L a to the power L PL is equal to C minus C minus E0 AP1 E0 AP1 plus summation over L BL a to the power L plus 1 PL. This is an identity in PL. So the coefficient of P0 gives you A0 is equal to C plus B0 by A. The coefficient of P1 gives you A1A on the other side minus E0A plus B1 by A square, or A1 is equal to minus E0 plus B1 by A cube, and the coefficient of PL greater than or equal to 2 gives you AL a to the power L is equal to BL a to the power minus L plus 1, or BL by AL BL by AL is equal to a to the power 2L plus 1. So these are the three results. We just keep a summary of this. This will be needed in A0 is equal to C plus B0 by A. A1 is equal to minus E0 plus B1 by A cube. B1 by A cube and BL by AL is equal to A to the power 2L plus 1. There are another boundary condition to be satisfied, that is the boundary condition regarding the normal component of D vectors, which in this particular case, as we have discussed in earlier situation, that it is I del phi 1 del R at R is equal to A is equal to minus if we differentiate this expression, we get, so firstly we are no more bothering about the minus sign. We have removed minus sign from either side. If we differentiate this, we have EI AL L a to the power L minus 1 PL of cos theta. If we differentiate r to the power L, we have L r to the power L minus 1, which at r is equal to A becomes this. Now if we differentiate the right hand side with epsilon E, if we differentiate, this part is 0, this part is minus E0 P1, and if we differentiate this part, we will have summation over L BL L plus 1 a to the power minus L plus 2 PL of cos theta. If we differentiate this with respect to R, this is 0, this is minus E0 P1, this is minus E0 P1. The entire thing has been multiplied by epsilon E, permittivity of the external region, which is generally the permittivity of free space, epsilon 0. And if we differentiate, this one is minus L plus 1 BL r to the power minus L plus 2 at r is equal to L. This becomes, which is E0 P1 plus summation over L BL L plus 1, so a to the power minus L plus 2 PL. This is again an identity. Identity in PL. So coefficient of P to the power 0. P to the power 0, coefficient of P0. This is A0 times 0. So this is on the left hand side we have 0. On the right hand side we have minus epsilon E times B0 by A square. This part, this is L is equal to 0, B0, L, this is 1 and this is A square. So this gives you B0 is equal to 0. This gives you B0 is equal to 0. As B0 is equal to 0, A0 is C. So A0 is C. Coefficient of P1, this is epsilon I, A1, this is A1, this is 1, this is A to the power 0, minus epsilon E times E0 plus, this is 2B1 by A cube. And the coefficient of PL with L greater than equal to 2 gives you AL L a to the power minus L plus 1. This term does not contribute, so the other term contributes. L plus 2. Here from we get BL by AL is equal to minus, oh here I have missed epsilon I. Epsilon I times L L plus 1, and when this goes to the other side, this is A to the power 2L plus 1. And this relation can be written as A1 is equal to minus epsilon E by epsilon I or rather we write minus E0 minus twice B1 by A cube. So we write the other three relations. First thing is B0 is 0. B0 is 0. Then we have epsilon I by epsilon E A1 is equal to minus E0 minus 2 B1 by A cube. And lastly, BL by AL is equal to minus epsilon I L epsilon E L plus 1 e to the power 2L plus 1. Let me now analyze the result. If we apply B0 is 0, so these two gives you, these two relation gives us A0 is equal to C. And if we consider these two relations, we get it 1 is equal to BL by 1 is equal to minus epsilon IL epsilon E L plus 1, or epsilon I times L plus epsilon E times L plus 1 is equal to 0. The permittivities are the essentially positive quantities, and L the L ranges from 0 to infinity, positive non-negative values. So this can never be 0. This unphysical relation has been obtained from the assumption that for L not equal, L greater than or equal to 2 is non-zero. When we divide these two, it is in our mind that AL is not 0. That means that AL not equal to 0 is not correct, is not a correct assumption. That is, AL for L greater than or equal to 2 is 0. Similarly, the BLs are 0. So our conclusion is AL greater than equal to 2 is equal to 0, equal to BL L greater than equal to 2. So the only thing that remains is this part, and we can solve A1 and B1 in this term. This is minus 3 epsilon I epsilon E plus twice epsilon I is 0, and B1 is equal to epsilon I minus epsilon E plus twice epsilon I is 0. If we solve these two, now we see that only A0 and A1 are there for internal region, and for external region only B1 is there. So the this potential, if we write, keep the values of A1 is equal to minus 3 epsilon I 2 epsilon I plus epsilon E0, and B1 is equal to epsilon I minus epsilon E twice epsilon I epsilon E is 0. And A0 is C, and A0 is C. This is the condition, and all other A's are 0. So the potential in the internal region, for internal region, simplifies to, this is phi internal at r theta is only A0, which is equal to C plus A1 r cos theta. So this is C minus 3 epsilon I twice epsilon I epsilon 0 r cos theta. And for external region, we have, this is external region C minus E0 r cos theta plus only B1 term, B1 r to the power minus 2 cos theta. So this is C minus E0 r cos theta plus epsilon E epsilon. This is the potential. Two things is of interest. If we consider this is the potential due to the external field, so the phi 0, and this part is the induced potential, the potential due to the induced pair. Obviously this is a dipole potential. So far an external point is concerned, the induction effect can be taken care of by this dipole term, and we can define dipole moment and the polarization vector from this. Because the dipole potential is phi dipole, as we have done in the other class, is 1 by 4 pi epsilon E P cos theta by r square, where from we identify 1 upon 4 pi epsilon E P as this part, and the dipole moment and polarization can be obtained as we have done in the earlier class. Another interesting thing is the electric field itself. The electric field E in the internal region is given by minus grad of phi internal, and for external region we have this. For the geometry under consideration, this is minus k cap del phi E del z. This is the field. This part is the z part. It is the z part. So this is z part. So if we differentiate this, we get this minus and minus cancels out. This is k cap 3 epsilon E. Oh, I have missed E0 part over there. E0, that is to say this is 3 epsilon I, 2 epsilon I plus epsilon E times E0. Now, in general, epsilon I is the permittivity of the dielectric medium or the dielectric constant, which is greater than epsilon E, which is the S0 vacuum. So to say, I am really sorry for this mistake. It should be E. You just solve this one of yourself and you will see that this is E. So since this epsilon I is greater than epsilon E, we see that this part is less than 1. That is, we conclude that the field within the dielectric material is less than the field outside. So in the vacuum the field is greater, and within the dielectric medium the field is small. This is due to the fact that the polarization charges, the positive charges are induced in this direction and negative charges are induced on the other side, and this polarization, induced polarization, tries to oppose the existing field, so the field within the dielectric medium is slightly less than the field in vacuum, wherefrom we can define the demagnetizing field demagnetizing field as we have done in other classes.